Hello everyone, this is example 8 on statical stability of floating bodies. So here we go, a rectangular raft 3 meters wide and 6 meters long has a thickness of 0.6 meter and is constructed of solid timbers having a specific gravity of 0.6. If a man weighing 890 newtons steps on the edge of this raft at the middle of one side, how much in mm will the original water line on that side be depressed below the water surface? So this is the given figure. The draft without the man is zero point 0.6 of zero point 0.6 because this is zero point 0.6 of 0.36 meter. So the weight of the raft alone is specific gravity of the raft times specific weight of water in newtons per cubic meter times volume of the raft 3 times 6 times 0.6. So it is equal to 63,568.8 newtons. With the presence of the man, the total weight, which is also the total buoyant force, would be 63568.8 plus the weight of the man, 890. So it is equal to 64,458.8 newtons. Now, with the presence of the man, the raft is already depressed by 890 equals buoyant force, 9810 times 3 times 6 times delta 1. So the man can depress if he stays at the center by 5.04. Now in the tilted position is now the position of the man. Take note that the center buoyancy moves sidewise. So this is now the new position at BO prime. Then this is the original weight of the raft. Then this is the weight of the man. Then the new draft with the presence of the man would be 0.36 plus 0.00504. So that's why you have here this value. BO is half of 0.36504 from the bottom. Therefore, the distance of the top edge from the center of buoyancy is 0.6 meter minus 0.36504 over 2. So you have it there 0.41748 meters. The center of gravity of the raft is 0.3 meter from the bottom and from the top. Therefore, the distance between center of gravity and BO would be 0.3 minus half of 0.36504, which will be shown later when we sum up moments about BO. So let's compute for MBO in terms of theta, b squared over 12d times quantity 1 plus tangent squared theta over 2. So it is equal to 3 squared over 12 times 0.36504, 1 plus tangent square of theta over 2. So MBO is 2.0546 times 1 plus tangent square theta over 2. So we use the principal summation moment about BO equals 0. So 64458.8 times 2. MBO sine theta. So this is MBO, then sine theta equals moment of the 890 Newton man. The component, this component parallel to this is 890 cosine of theta, and the moment arm is 1.5 plus 890 sine theta times 0.41748 plus the moment of the weight of the raft 63,568.8 times quantity 0.3 minus 0.36504 over 2. That distance there times sine of theta. So combining sine theta, we have this value times sine theta minus this value, you'll have 124597.47 sine theta, then 64458.8 times 2.0546 divided by 2 is 66,218.53 tangent square theta sine theta. Then at the right side, we have 890 times 1.5 cosine theta, or 1335 cosine theta. So solving for theta in this equation here, using a high-tech calculator, so theta is 0.6138 degrees. So tangent to 0.6138 degrees is equal to delta over 1500 mm or 1.5. So delta in mm is 16.07. The total depression therefore on this side of that edge is 5.04 plus 16.07. So total depression is 21.11 mm. So this problem can also be solved approximately, and total depression will vary a little, but very little value, but it is still practical. So we ignore the moment of this weight here, and the moment arm of 890 is just taken 1.5 because theta is very small, and you will arrive at very close results. So that's the practical approximate solution. This is just the accurate solution, but the solution needs numerical techniques because of this equation here that can only be solved by using a high-tech calculator. So that's it for this problem.